Okay, so welcome to this next video in which we are discussing sensitization. Okay, so we're currently discussing the sensitization of the gill withdrawal reflex within Aplysia californica. Okay, so we want to now see how the L29 neuron, which remember is activated by the delivery of the electrical shock to the head of the Aplysia californica, okay, how that's going to trigger the increase in the release of neurotransmitter by the axon terminal of the L1 sensory neuron. Okay, so here is the axon terminal of the L1 sensory neuron, and then we're going to have the axon terminal then of the L29 neuron here, which is an interneuron. Okay, so remember the L29 neuron makes this axo-axonic synapse with the axon terminal of the L1 sensory neuron. Okay, and we now want to see how the activation of this L29 neuron is going to increase the release of neurotransmitter by this L1 sensory neuron here. And basically, L29 releases the neurotransmitter serotonin onto the L1 neuron. Okay, so let's start with a discussion of serotonin. Now, the other name for serotonin is to call it 5-hydroxytryptamine. Okay, and this reflects the fact that 5-hydroxytryptamine is a modified version of the amino acid tryptophan. Okay, so let's have a look at the structure of the amino acid tryptophan, and then we'll see how to create tryptamine, and then we'll see how to create 5-hydroxytryptamine. And now, before we see the structure of tryptophan, what we should discuss is the structure of the Pyro Ring, as well as the structure of the indole ring. So I'll start with the structure of the Pyro Ring. So basically, let's draw the skeletal structure of the Pyro Ring. So the Pyro Ring is a 5-membered ring where one of the members is nitrogen. Okay, so you have a nitrogen right at the top here, and the other 4 members of this ring are carbon atoms. You then have a double bond between this carbon and this carbon, and also a double bond between this carbon and this carbon, and then we just need to show the hydrogen coming off that nitrogen. Okay, so that's the structure of a Pyro Ring. Basically, an indole ring is just a Pyro Ring with a benzene ring stuck off the side of it. Okay, so let me show this. So here's this 5-membered ring here. Got a nitrogen at the tip with a hydrogen coming off it. Then we've got a double bond here, a double bond here, and then we're going to have a benzene ring attached here, like so. And we'll have a double bond there and a double bond there to give us overall alternating double and single bonds. So this is an indole ring. Okay, right. So now we're in a position to look at the structure of tryptophan, because basically tryptophan is just a methylene group with one of these indole rings on it. Okay, right. So I'm going to suddenly go from drawing skeletal structures, as we've drawn here, to drawing a kind of mixture of skeletal and molecular structures. Okay, so here is the core amino acid structure, okay, that's common to all amino acids. And then the R group of tryptophan, you have a methylene group like so. And then attached to the methylene group, you then have this indole ring, okay, like so, which remember is this 5-membered ring, which is the Pyro Ring, with the benzene ring attached to it. So here's the Pyro Ring, and now we're going to have the benzene ring attached off here. Okay, and we have a double bond there, double bond there, double bond there, and a double bond there. So this is the structure of the amino acid tryptophan. Okay, right, but we want tryptamine, and then we want 5-hydroxytryptamine. Right, so to understand how we're going to get 5-hydroxy, what I need to tell you about is the naming system for the members of the indole ring. So basically, this nitrogen here is named number 1, this carbon here is named 2, this carbon here is named 3, this carbon here isn't named 4, but instead is called 3A. This carbon here is called 4. This carbon's called 5, 6, 7. And again, this one that's shared in between the 2 rings isn't called 8, but is called 7A. Okay, so that's the naming system for the members of the indole ring within the tryptophan structure. So we can understand that to get the 5-hydroxy, all we're going to have to do is stick an alcohol group off this 5th carbon, so that's easy enough. But how do we turn tryptophan into tryptamine? Because we don't just want 5-hydroxytryptophan, we want 5-hydroxytryptamine. And the way that you turn tryptophan into tryptamine is by removing the carboxylic acid group here. You remove that and replace it with a hydrogen, and that creates you tryptamine. Okay, so let's now draw out the structure then of 5-hydroxytryptamine. So here's the amino group, here's the alpha carbon. The alpha carbon now has a hydrogen coming off here to replace the carboxylic acid group. You then have this methylene group still, and then we have the indole ring, so I'll draw the indole ring here, okay, like so, which is this 5-membered pyro ring, then with the 6-membered benzene ring coming off the side. So you have a double bond there, a double bond there, and you have the benzene ring up here, like so. Okay, and then you have a double bond there, a double bond there, and you have an alcohol group coming off this 5th carbon up here. And that then is the structure of 5-hydroxytryptamine, which for short is abbreviated to 5-HT. Okay, right, so this is the neurotransmitter that this L29 interneuron is releasing onto the L1 sensory neuron. And basically what the L1 sensory neuron will have on its surface is a G protein coupled receptor for 5-hydroxytryptamine. Okay, so this is our G protein coupled receptor with the characteristic 7 membrane spanning alpha helices. Okay, so this is the 5-HT receptor. Okay, right. So we'll draw this in a bit more detail down here. Okay, so if this is the phospholipid bilayer, so I've gone from representing the membrane by 1 line to representing it by 2 lines, representing the inner leaflet and outer leaflet of the phospholipid bilayer. Then we have a G protein coupled receptor on the membrane of the L1 neuron, okay? And this G protein coupled receptor will bind to the 5-hydroxytryptamine. Okay, the G protein coupled receptor will then be coupled to a heterotrimeric G protein, and that heterotrimeric G protein, when activated, will lead to the activation of an adenylyl cyclase enzyme. Okay, so I'll just draw this like so. So it's going to activate an adenylyl cyclase enzyme, which will be in the membrane of the L1 sensory neuron. And this will then convert ATP to cyclic AMP and pyrophosphate. Okay, so you'll start producing cyclic AMP and also pyrophosphate molecules. Okay, and cyclic AMP is then going to activate protein kinase A within this L1 sensory neuron. Okay, now what does the protein kinase A then do? Well, basically it phosphorylates a potassium channel and causes that potassium channel to close. Okay, right. So here's a potassium channel. Okay, like so, coloured in purple here. And basically, what's going to happen is protein kinase A is going to phosphorylate this potassium channel, and that phosphorylation, so I'll draw the phosphate group here that's been added on to that potassium channel. That phosphorylation causes the closing of that potassium channel. Now, what's the effect of closing a potassium channel? Well, basically, what it causes is the prolonging of action potentials, and let me explain why.